So it's a great pleasure to be here. Thank you very much for the invitation. Let's see if I can change. Yeah. So the main goal of my talk is to present some preliminary, please notice that I put it in red, attempts at applying the Beisel-Eden-Staudacher analytic continuation trick to other theories, not n equal to 4 superior means in particular. I am particularly intrigued by theories with less supersymmetry, even zero supersymmetries like large N QCD. This would be the sort of main part of the talk, but before that I would like to make some comments about the status, what I think is the status of integrability for this theory. So by this theory I mean large N QCD, not n equal to 4. So the plan of my talk will be to start with a brief review, just a few transparencies of some previous old results that we obtained on one loop integrability of large N QCD. Then I will move on to show how integrability actually fails at 2 loops for this theory. So I held for quite a long time the hope that it would be possible to extend these results to higher loop, and I will explain why I had that belief, but I now have convinced myself that this is not going to work. But then to cheer you up and to cheer myself up, I will argue that perhaps after all the anomalous dimensions are not the most interesting quantities to look at in a non-conformal field theory. There are many more there is much more information to be gained from the, say, the correlator between 2 gauge invariant operators than just the anomalous dimension. And so we'll move to the second part of the talk, which is, I repeat, more preliminary, and which will be to introduce some relevant facts about the 2-point functions, to try to put the BES trick on some more solid footing, for at least to argue that it can be sort of taken seriously even in this case, and to try to apply to the 2-point function of gauge invariant operators and see what happens, or at least what might happen. I'm going to do this many times, I'm afraid, because I'm the only one who gets confused by this, I guess. Yeah. So, all right. One loop. So this is all the result with Nicholas, Reiner, and Kostya a few years ago, and I will not give references to. There is an enormous amount of literature by many people in the audience on integrability in theories in QCD, in large N QCD, or QCD even without large N. I will be brief also for time reasons, and also for my somewhat inability to present the whole history of the subject, which is rich and very interesting. I will just present the part of the work that we have done, which is okay. So you define a field strength. This is the field strength of large N QCD. So think about pure Yang-Mills. The quarks, as we know, the quark C is suppressed at large N. So you can think of it as a pure Yang-Mills theory. So the connection is an n by n Hermitian matrix. You let n go into infinity. This is the curvature. G Yang-Mills is G Yang-Mills. You decompose the F mu nu into the chiral, and I call it chiral, anti-chiral. I should call it self-dual, anti-self-dual part. This is really the self-dual and the anti-self-dual part of the field strength, and of course in the Van der Waals notation in the dotted and undotted indices. And you do the same thing with the covariant derivatives. And you look at this theory and you take the 't Hooft limit. That is, you let n go to infinity, keeping this quantity, which is the 't Hooft coupling, constant. So what happened at one loop? A basis of first of all, you look at single trace gauge invariant operators. As we have learned from the work of Kostya and Joe, you can construct gauge invariant operators that look now like spin chains, where these are the words, the single trace operator, and each letter making up the words, each x, is simply in this case is a subset, it's a subclass of all the letters that make up n equal to 4 superior Yang-Mills, and in this case is simply an arbitrary amount of covariant derivatives acting on F, either the self-dual or the anti-self-dual part, and then you have to play a little bit with the equations of motion, and you realize that in order to have a complete but not over-complete set of observables, gauge invariant operators, you may take the totally symmetrize, you have to totally symmetrize in the dotted and the undotted indices separately. So this is the set of letters that you can use to make up these words, and then you remember that at one loop, even super QCD, even large N QCD has an effective conformal symmetry. And in fact, just by working out by brute force the anomalous dimensions of the matrix of, for this operator, you realize that it is the spin chain of an Hamiltonian based on the conformal group. This is, of course, a one-loop result. And that, and then you study it, and you look whether it's integrable or not, and it turns out that the full spin chain, so the spin chain made out of all the possible combination of these operators, already to one loop, is not integrable, but there is a closed sector to one loop, and which turns out to be integrable, which essentially is the purely chiral operator. So it's the operator made out of only the self-dual part of F with an arbitrary number of derivatives. And just the results that you get if you study the spin chain is just now reduced to a condensed matter problem, and you realize that actually the ground state is quite fun. It's a rather it's the antiferromagnetic state of the XXX1 spin chain. So if you that is the ground state is made out of those operators without derivatives, and without derivatives really the F is just a spin 1 object. And so you end up with an XXX1 spin chain, which is antiferromagnetic. So you can actually use all the beautiful results in the condensed matter literature about these things. And then you can study the excitations, and the excitations are spinons of the XXX1 chain. Again, beautiful literature in condensed matter, and magnons, which put it between quotes, that are something extra, something that goes beyond the XXX1 spin chain, which involves putting derivatives, sprinkling some derivatives, and making them move a la BMN, let's say, along the chain, and the dispersion relation for the spinons is linear, and for the magnons is quadratic. So now the, yes?
What is the spinon in terms of operator?
Oh, it's a very complicated, already the ground state is an antiferromagnetic ground state, so it's a sum of many, many terms. It's a spin 0. So it's the spinon of the XXX1 spin chain. It's a very complicated object, actually. We can discuss it later. But there is you can be as explicit as you want, but there is no sort of one-liner to describe it. At least I don't know it. It's a rather... Right. So that was old work that I just wanted to introduce you to, but there is of course a critique that you can make of that word. The first one is, okay, very good, but this is just a one-loop result. Also in a non-conformal field theory, the anomalous dimension, first of all, what do we mean by anomalous dimension? We mean the gamma that appears, I should have said at the very beginning, the gamma that appears in the current semantic equation, the RG equation. And we all know that is not, they are scheme dependent at higher loops. Only the first loop is universal. And in addition, there's always been the thing that I wanted to test. Integrability is probably lost. In fact, it turns out it is. But there is also another element of the critique of looking at these objects for non-conformal field theory, which actually turns out, I think, to be a bit of a saving grace, which is the fact that, contrary to conformal n equal to 4, as I said in the very beginning, in a confining theory, the anomalous dimensions are not the most interesting part of the correlation function. And one would like to say something more about, for instance, the position of the resonances and all of these things. Let me first tell you a little bit about why I am now convinced that integrability does not survive to higher loops for this theory. This transparency is something that sort of was constructed during a conversation with the chairman, but I didn't have the place to put your name, because otherwise this equation would have gone out in the other transparencies. So, well, first of all, at higher loops, one would think that everything is hopeless, because we already know that the theory is not integral to one loop, because the chiral and the anti-chiral sector, when they mix, break integrability. But then you say, well, but look, I mean, at 2 loops already, they do mix. Because look at these 2 operators, which are very simple. This is the Lagrangian, and this is the topological density, which written in the undotted indices are just like this, with a plus and a minus, okay? Now you know that it's a very, very well-known result from quantum field theory. This essentially is the trace of the stress energy tensor, and this is the topological density with the proper rescaling of the lambdas. These 2 objects are not renormalized. Then by hitting them with a mu d nu, you can immediately work out the anomalous dimensions for these 2 operators to all orders in lambda, given a renormalization scheme. That is, if you give me a way to compute the beta function, which in my words is like it's a scheme, then in that scheme I know the anomalous. In other words, I know an exact functional relation between the beta function and gamma. This is also very, very well known results from quantum field theory. I learned it from a paper of Morozov, but I don't know actually what is the original of this. It's in the books now, you immediately see that. Indeed, they are the same to 1 loop, and this is really one of the reasons why the theory is integral to 1 loop, but they are not the same at 2 loop, no matter what the beta function is, and at any rate, the beta function, the first 2 coefficients are universal anyway, so there isn't much you can do. So
does this mean that these particular anomalous dimensions are universal to 2 loops?
No, I don't. Well, oh, good point. Let me say yes, and we can discuss it. If you now, I didn't think about that. I didn't think about that.
Sorry,
but
what's the question?
The question is, does this mean that these 2 anomalous dimensions are universal at 2 loops that do not depend on the renormalization scheme? So now the situation seems hopeless. However, the situation is not that simple, because there is a chiral subsector that is closed to all loops, and it's made out of the following letters. If I take the chiral operators, but I decide not to turn on the alpha equal to 2 index, I turn off the undotted alpha equal to 2 index, and notice that neither the Lagrangian nor the topological density belongs to this subsector. This subsector is closed to all loops. In fact, we all read Nicholas' thesis. This is, it turned out after I went back and read his thesis, it's in there, of course, and it's the 0,4 sector in n equal to 4. For those of you who know what this notation means, it's essentially you turn off all the fermionic oscillators and the alpha equal to 2 oscillator. My own way of this theory is much simpler in a sense. So it's a very easy way to see closure is to just realize that the commutator of 2 covariant derivatives is written like this. If I decide not to turn on one of the 2 alpha indices, then this term is killed, and I get this fact here. So this sector is indeed closed. It's closed to all loops. It's integrable to 1 loop, and it does not fall into the counterexample that I showed you in the previous transparencies. I'm afraid of going back because. Yes, okay. And it doesn't belong to this. So, so in the light cone notation, if you wish, this is the same. This is just an aside. In the light cone notation, essentially, we know that the light cone operators are not closed in Purian-Mills, but this object is. In a sense, what you're doing, you're just expanding these 2, the f plus z, say in the light cone gauge A plus equal to 0. This is just an aside. I won't go into the details. And the light cone derivatives. These 2 objects would make up the light cone operators. These are not closed, but if you add the possibility of taking the covariant derivative with respect to AZ, where AZ is the A1 plus IA2, then this is essentially the sector that I'm talking about, and it is closed. And it's closed to all loops, and it's integrable to 1 loop, and then the question is, yes, but is it integrable to higher loops? Well, I really hoped it would be, and there are tantalizing similarities with work by Belitsky, Krochemsky, and Müller, where they have done a similar analysis for n equal to 2 superior Mills, where they show that, in fact, parity degeneracy survives, and so on. But I don't think this is going to work in this case, and I'll tell you why. There is really a very sort of simple argument. let us test perturbative integrability for this theory. So let us expand the Hamiltonian into the one loop Hamiltonian plus the, let me call it 1.5 loop and the 2 loop Hamiltonian. And then let us take the second conserved charge and do the same thing. And this is the test of perturbative integrability. To one loop, we want to check that the first two terms. Essentially, you set to 0 all the components of the Taylor expansion of this, or the commutator of H and Q, as you all know very well. Now, let's see what happens in our theory. So, as I said, so the green objects are the objects in n equal to 4 super Young Mills, which are nothing but, as I said, the 0,4 sector, which is truncated to just the pure gluonic lines. So the n equal, so in the one loop case, one of the reasons really why the large N QCD was integrable is that its Hamiltonian, its worksheet Hamiltonian, is really nothing but the one of the n equal to 4 shifted by the fact that when you normalize all the legs, you have some wave function renormalization which is not there, because these are the fermions and these are the scalars of n equal to 4. They're just not there in pure Young Mills, and so these are the diagrams that you get in pure Young Mills. These are the whole thing are the diagram that you get in n equal to 4, and there you go. N equal to 4 and pure Young Mills at one loop are simply related by a simple identity operator which summed over the legs gives you L. The 1.5 loop is even simpler because essentially they're the same. They're the same because this is the 1.5 is the one that changes the length of the chain by, say, adding or subtracting a letter. In this case, look at the one that adds a letter. So all the diagrams, since they have to have gluons coming in and gluons going out, well, there is no room for any other particle. So these two diagrams are identically the same. What happened to the first conserved charge? It's even there, it's actually the same thing. Now, this is the well-known expression for the local first conserved charge other than the Hamiltonian in terms of the Hamiltonian itself. So these bubbles here are all objects that appear in the Hamiltonian, and it is well known that the first conserved charge can be written in this way. Now, if you replace, well, if you put here either the n equal to 4 or the n equal to 0 Hamiltonian, you're going to get the same result because of this minus sign, and the identity matrices will cancel out. So these two objects are identically the same. Now, actually, it turns out this is a less known fact. It's, we constructed in a paper with Agarwal about a couple of years ago. You can do the same thing for the higher charges, really. We don't have a rigorous proof that this works in n equal to 4 to all orders, but we have a construction that works for the SU2/3 sector, which is the simplest sector that changes the length of the chain. And it's not that difficult to show that this is what something like this does the job, where these bubbles again are the one loop and the 1.5 loop Hamiltonian. And again, it turns out that because of the cancellation due to these signs, the adding a shift to the one loop Hamiltonian doesn't change anything. So, so let's check. Doing it one loop, you commute the Hamiltonian with the first charge, and you get the n equal to 4 result, which we know being 0 by integrability, and then you get the commutator of the length with the first, with Q0. Since Q0 conserves the length, this is 0. But already at 1.5 loop, you get into trouble, because if you now take the commutator between the Young Mills, the large N Young Mills charges and Hamiltonians, you get, and you express them into the n equal to 4 objects. Now the n equal to 4 piece cancels, but then you're left over with this. But Q1, well, Q1 does not conserve the length, because it turns 4 legs, I mean 4 objects into 3, or vice versa. Therefore, in fact, this thing does not commute. So this is, to me, a very strong indication that there is no perturbatively integrable sector in large N QCD. Now, I don't say this is a proof, because one possible loophole which I personally don't believe in, is that maybe you have to change the expression for Q1. I did try a little bit with some numerical simulation, but it doesn't seem to work. So this was the first part of the talk. Now I want to move. It's probably a good time to stop and ask if there is any question about this, because
Do you understand correctly that you have mixing of sectors with different number of particles?
yes, different length.
Right. Well, if you'll consider one of the components of the cell-to-all strength tensor, like for instance 1, 2, and 2, 1, it will be the length, well, just helicity gluon, right? Specific helicity gluon. And we know that at 2 loops, the line helicity operators, they form a closed sector. So presumably those transitions where you have change of number of particles will be suppressed, actually they won't be there. Well, it's true only to 2 loops which are considering. Beyond that, this sector is not closed.
We can talk suppressed in what?
Huh?
Suppressed in
Well,
what?
they're not there. Those transitions are not present. 2 to 3 or 3 to 1.
No, that's right. 2 to 3 and 3 to 1 are not there, but
So do you have those transitions? Do they contribute to the mixing matrix? In your case,
yes, they do.
they do.
Yes, they do.
So do they yield the?
Yes, they do. But they're there. They're there in the 4,0 sector as well, because so
Well, but they're not in the aligned.
not in the maximal helicity.
Right.
Yeah, no, that is true. In those cases, they're not there. But then, yeah.
So you might have integrability, but in a small subsector of QCD.
But that subsector is not closed.
Which one?
The one, the sort of the maximal helicity.
Oh, it's closed. To 2 loops, it is.
To 2 loops is closed. Yeah, no, but I'm talking about. Yeah, we can talk about this later.
exactly
But
what-
yeah, to 1 loops, it's yeah. We can discuss this. So let me change subject completely now and discuss some what the actual title of the seminar was, which is a very preliminary attempt at playing a different game, completely different game. Let us consider. So let us accept that very likely this theory is not integrable, at least in this sense, and look at another aspect of this theory. Let us define, as we all know, take any gauge invariant operator. Let us take the Lagrangian, for instance. Could be anything. Could be usually people take the currents for the quarks. But let us consider the 2-point function, or the Fourier transform of the 2-point function of this operator. Now, this will be given by dimensional analysis. Well, in this case, this is dimension. There will be a p to the 4. P is the momentum in front of everything, and then there will be this Fourier transform will be given by a dimensionless function of 2 variables, lambda, if you calculate it in perturbation theory, lambda, and t, where t is just the log of p over mu, and mu is the renormalization scale. This is a function of 2 variables, but we know that from any quantum field theory book, the renormalization group equation applied to G means that G really is not a function of 2 independent variables, but it's a function of 1. In other words, the RG equation can be solved, and it can be solved in 2 steps. First, you introduce a running coupling, so lambda hat by solving the Gell-Mann law equation. So lambda hat is the running coupling, and lambda, which will be the one that I will use in all of the following. So I will not use the running coupling. I will use this lambda, which is essentially the initial condition, which I now put at t equal to 0, so in the strong coupling region. Okay. If I have the beta function exactly, I mean this, the point is that this equation is not a perturbative equation. You should think of this as an if you knew the exact value for beta and lambda, this is an exact equation. So you can play this game, and you can say then that the solution to the RG equation is given in terms of a function script g of just 1 variable. And this is the important piece of the correlation function, not as much this tail here that has to do with the presence of the anomalous dimension in the RG equation. So in the Lagrangian limit, we know that this function is actually saturated by an infinite number of 0-width resonances. Up to subtraction, I can, so this can be written in many ways, but one way to write it is this. So there will be an infinite, in every channel, there will be an infinite number of resonances of mass m of r. So with r is an integer that labels the levels of the resonance. Simple as that. So I'm summing over r between 1 and infinity. Infinity is from the large n limit. And just the fact that this thing has to be a normalization group invariant, it means that the masses will be expressed in terms of a RG invariant scale lambda QCD, which obeys the RG invariant scale, which therefore we can solve it to be like this, times some real coefficients, nu of r, some monotonic sequence that goes up. And also the same thing can be said for the residues, and the residues are also z of r, one for each resonance. It tells you, what is the coupling of these objects. And this is a sort of well-known fact. Now let us, so I would like to see if I can say something about this little g. Let us set p square equal mu square, that is, let us set t equal to 0, and look at this function, which is now a function of lambda. This is a sum of infinite terms of this type. So well, before I go further, let me tell you let me remind you what the expectations from the large and limit are. From the string picture, or just simply from Born-Sommerfeld quantization, we know that in a linearly confining potential, the masses square are rising as integerly spaced at large r. This is a well-known fact. And then depending on the subtraction, we know that because the sum over the infinite resonances must give rise to a logarithmic to a logarithm in p, we have that we have to take this z of r to go to 1 over r at large n. This is just essentially the expectations from the string pictures of these interactions. Now, let me consider now a greatly oversimplified version of this thing, just to show the idea. Okay, focus on the idea more than on the calculations, because the calculations certainly leave great room to improvement. But this is I'm trying to present the idea here. The idea is the following. So at one loop, lambda QCD essentially is given by mu times minus 1 over 2 B0 lambda. B0 lambda is the beta function to one loop. So my function g, the function that I would like to get to, which depends on this unknown series, increasing series nu of r and z of r, can be now expanded with very little work, can be expanded into a power series of 1 over lambda. Strong coupling. So I will call this coefficient here that gives me this expansion as x of L. And now I will close my eyes and pray my luck that I can apply the BES trick, and at least I try to do it and see what happens. So I remind you that the trick is that of turning an asymptotic expansion in 1 over lambda, say. And this trick has served us very well, as we know, in n equal to 4 in the determination of the...
so what is your dimensionless parameter?
Lambda, little lambda.
What is that?
Is lambda 2.
QCD.
Yeah, okay, so in QCD, well, that's, you see, this would be the strong coupling point. So this is, Is
it even defined?
Well, there will be objections here that you have. I made a couple of lists full of objections, but yes, it's a good point. But
certainly not a free parameter.
Yeah, it's not a free parameter. It's not a free parameter. However, let me carry on and see. So okay. First of all, you could have even argued something even worse. You cannot trust the one-loop beta function for large lambda. Even if large lambda was defined for large lambda, you still could not define the.
I think defining what lambda is before that.
Yeah.
Before making any statement with it.
But in the large limit is not, to me, is not entirely clear that you cannot play that game. We can discuss this, but there are certain things that I mean, a formal expansion. So remember, this lambda is not the running coupling. This lambda is essentially the initial condition to my Gelman law equation.
There's only one Yang-Mills theorem that doesn't have any
I-
parameters of the domain.
We can discuss this. So another point that you can argue about is that, of course, the beta function should not be trusted. But then again, in the Lagrangian limit, you have a better convergence property for the observables around lambda equal to 0. And this is true already at the level of matrix models in 0 dimensions, and you can argue that perhaps this you can find a scheme where you will find a beta function that is analytic around lambda equal to 0, and you can continue this way. Other problem is that there is, of course, each term here, and this is actually related to what you're saying, each term here has actually an essential singularity at lambda equal to 0. In other words, if I were to expand this naively in powers of lambda, I would get that when lambda goes to 0, these are all zeros. But this is again another point where the Lagrangian limit is crucial if this idea has any chance of working, because what I'm really doing here is to sum over an infinite number of resonances. So the hope is that there is some trick that you can play with the sum that that might allow you to make it work. There are more potential objections, but before I tell you briefly what happens in how much time do we have? 10 minutes. Okay. Before I tell you briefly what happens if you try to apply this trick, let me just try to sort of remind you a little bit about this. Maybe Nicholas has talked about how you can take this trick, how you can make this trick about going from the strong coupling to the weak coupling expansion a little bit more serious footing. So forget QCD now for the time being, and consider an analytic function f of z having at most isolated singularity at z equal to 0 and z equal to infinity. That means that I can make an expansion in powers of z around in some finite region A, around, like bounded by z equal to A around 0, and same thing at infinity. And there could be a lot of singularities in the middle. And of course, A of n and B of n are given by this contour integral, where the curve can be any curve sitting inside these two regions. The main point that I want to make is that if I consider this object, C of n, which is A of n minus B of minus n, this function of n, of integers, as a natural analytic continuation for all n's, because the factor z of minus n, which sits here, can be made analytic in n by moving the branch cut of z away from the singularities. So let me tell you in pictures what happens. So this is the initial contour of integration. This integral here is what gives me B of n, A of n. This integral here is what gives me minus B of minus n. I make a cut like this. I shrink the contour on the singularities, and then I make a branch cut for z to the n that goes to infinity without hitting any of these little contours, and so I can argue that this is a good choice for analytic continuation of this quantity. Now the last piece of this is something you can always say, but there is another ingredient that is an extra ingredient that is coming now. Assume now that this function has singularities at z equal to 0 and z equal to infinity, which are at worst poles. That is, assume that there is an integer big M such that A of n and B of m are both 0 for m less than big M. Then that means that if I take little n larger than the absolute value of big M, which essentially implies this, then I have that B is 0, which means that A of n is equal to C, to this function that I just argued as an analytic continuation. In the same way, if n is less than minus the absolute value of m, then this is also true, and then A of n will be 0, again because of this extra condition. And so you have this fact that you can essentially argue that in this case using this function C of n, you can make an analytic continuation and go from, if you have an analytic expression of these objects as a function as an analytic function of n, you can go back and get some predictions for the coefficients in the perturbative series. Then there is I'll skip the comment on the entire functions. So let's see what happens in the case of these correlation functions. So let us go back to our simplified case that I argued before. So now I choose my lambda to be, and I repeat that this lambda, is the initial condition of the running coupling constant that enters the Gelman law equation. And although there is only one QCD, I can still pick an arbitrary initial condition for this equation, and I can still claim that I can do see, I was thinking about your objection, so let me try to argue about this objection again. So since this is actually an important point, let us not confuse the running coupling again with this lambda, and this was something that I said before. If you take, it's absolutely true that the true parameter is big lambda QCD, is the dimensionful RG invariant scale. What I'm doing here, I am unraveling this lambda QCD. I'm doing something silly in a sense because I'm rewriting this lambda QCD as a function of two variables, the renormalization scale mu and the initial condition to the Gelman law equations lambda. I know that they will be combined into, given a certain beta function, they will be combined into an RG invariant dimensionful quantity. That is the only quantity that enters there. However, there is also a third player in the game, which is the momentum, P, that I inject with my operator. Now what I do something that you usually don't do. Instead of saying, okay, there is no coupling constant and I should write everything in terms of lambda QCD, which is the standard law, I set P equal to the renormalization scale. And I now look at the function G. That's why I actually think this trick may be completely wrong, but I think it is allowed to do that. I think of my function G, which is a function of one variable, not as a function of the renormalization coupling that you should ask me then again what is the value in QCD, but as a function of the initial condition, because I have set the momentum equal to at the renormalization scale.
So you've got a 2-point function which depends on a momentum P. You've got lambda QCD. So the only dimensionless parameter is the ratio. Is absolutely is.
But I think of the ratio not of P over lambda QCD, which is what you usually do, but the ratio P over mu, the renormalization scale. And that I fix to 1. And the lambda that is entering here is actually the lambda that it gives the initial condition. So it's a very non-orthodox way of doing things, of course, and it's not clear if it leads anywhere, but it's not inconsistent with what you're saying. But we can continue discussing it later on. So anyway, this is what I try to do anyway. So this is the initial X of L. This is our this is what you get by doing a naive expansion. I stress again that you shouldn't trust any of this in the concrete details, because this is a one loop. I use the one loop beta function, which of course you shouldn't trust, but this is just to illustrate how the procedure should go. So this is my X of L, and I just, as I said, close my eyes and I apply the BES trick. And what happens is that I turn L into minus L and I change the minus sign. So this is trivial, this just changes. The factorial becomes a gamma function, and then this becomes a double sum with k of minus L. Now, and I would like to argue that these actually are coefficients of a perturbative expansion. Now, since gamma of 1 minus L has a pole for L equal to 1, 2, and so on, in order to get a non-zero answer, I need the sum to develop a simple pole in L as well. I need this function here, which is some sort of Dirichlet series of some kind, to develop a pole at L, at integer L. so that this pole here would cancel the simple pole there. Now, again, this is where the large n limit comes to the rescue, I think, if this has a chance of working, because each single sum over k, if you just naively look at it, gives you what is called a polylog. This polylog, as it's usually defined, is a function with no poles for large L. But then again, I have to remember that I have to sum over the resonances, and this might hopefully give rise to this sum. I will do it in an even more disgusting way. And these are the last two transparencies, and I just fake it. I don't know if there is anything to it. I just fake it in this following way. So remember the definition of the zeta function. This is the zeta function. The zeta function is defined as an analytic continuing this sum. This sum converges only if the real part of S is larger than 1, but it gives an analytic function that can be continued analytically to all S, and it has a pole at S equal to 1. Obviously, if I had some coefficient series, if I had some more general Dirichlet series, I would get, for instance, if I have n to the m, then I have the zeta function that is S minus m. Now, S minus m, now the sum, of course, converges for S larger than m plus 1, and it has a pole at m plus 1. That's absolutely trivial. Now, if I had something even worse, like e to the n, well, this series doesn't converge. But then if you do some wishful math, and I don't assume anybody will take me seriously on this one, you expand the coefficient e to the function e to the n in a Taylor series, and then you switch the sum, and you think of this sum now as analytically continued to the zeta function. Now this actually does have the required properties. This function does have poles that go all the way to plus infinity at simple poles that go all the way to infinity at as in S. Okay, so this actually has a chance. Something like this has a chance of canceling the simple poles here. If you apply that, you get. Now that this, as I said, you get an extra sum over P, but then every time P is equal to L plus 1, L minus 1, I get a simple pole here, and that's what kills this guy. So essentially the sum over P, in the sum over P, only one term contributes, and that term is the one that kills the pole here, and I get something here that looks like looks like a rather weird, I admit, type of sum rule in the residues and in the masses that appear as logarithms for this beta function. Now, as I said, I mean you shouldn't take this part seriously at all, because to begin with, apart from the wishful math involved in the last two transparencies, it's also based on the assumption that I truncate the beta function at one loop, and I know I cannot do that. But maybe it can be put into two more serious footing. So let me make just some final remarks. So as I said, given the amount of adventurous math involved, I'm not taking the sum rule seriously. I'm just merely considering them as indication of what might be accomplished with this strategy. The sum rule here. Or the kind of things you get if you play this game can be played with a little bit more sophisticated. This was really the absolute most trivial way of doing it. You can do better than that, but still there is much work that needs to be done. But this type of sum rules that you get are somewhat on the verge of converging. There is something that go like 1 over r at large R times some logarithmic corrections. There could be some sort of analytic continuation in L that makes it converge or something like that. It's possible, but I don't know that for a fact. Maybe if they actually turn out not to converge, you can always take the difference between correlators, as it's traditionally done in the sum rules of Weinberg in the 60s. You can actually do the calculation with the two-loop beta function, which is actually more serious footing, because the two-loop coefficient is universal, and in principle, if you believe in the analyticity property of the beta function around lambda equal to 0, you can actually perhaps truncate it there. But at the very last, I hope I try to end on a poetic note. At the very last, I hope I have piqued your curiosity to take a stroll outside the n equal to 4 enchanted garden. Thank you very much.
Could you please show the previous transparent? Another one. Yeah, this one. And so this will just look last formula. So this formula tells you that, yeah, I just look for this formula and I see that perturbability of correction to your green function to L's order at decoupling expansion has this beta function power L times something. Now let's think about how could you get similar behavior from Feynman diagrams. We know that this beta naught, in particular gauge, will come from self-energy correction to the Bloom propagator, right? Just the only way to do it here. Therefore, we could immediately trace the origin of this correction to a very peculiar class of the diagrams, which are called inflated remote chain. And the consequence, we know that this sum which you have rows is sum of R. Its key is like L factorial. And as a consequence, the whole sum over L, this sum over L, doesn't make any sense.
This sum here, yeah.
This perturbative expansion is very non-summable. And then there is very old argument by Hooft that any expansion of this sort ought to be break down. This series has zero radius of convergence.
What is the series that has zero radius of convergence?
These coefficients, you just define, this formula defines the perturbative coefficients, the expansion of the green function of the powers of coupling constant.
Right.
Let's
For
think
the
about
for
this
the
coefficient.
for the 2-point function, yeah. But look, even if it was an asymptotic series.
Well, I'm telling you, this is a
Okay,
very non-summable series. And if it's very non-summable, I'm asking then the question of what's the meaning of the series.
Yeah, we can discuss about this. Even if it turned out to be an asymptotic series, you see, I would like to understand how much of these statements are actually concrete in the strict large n limit, the strict n equal to infinity limit, because
So you look for Schiffman and Weinstein Zahar of some rules.
yeah.
There's a paper back to 78 when people sort of more or less understood the structure of the theory.
We can talk about that. I mean, I know the paper, but again, I'm not entirely convinced that it applies 100% to this, but we can discuss this.
How's this related to integrability?
The second part is not really, unless, yeah, no. Well, unless you can always hope that there is some integrable structure that gives you these eigenvalues, but I don't have any evidence for
Can I
that.
ask? You see that in principle we can introduce not supersymmetry, but we can introduce in sufficient number of fermions in such way that first coefficient of beta function is close to 0. And second coefficient of beta function will be not 0, and therefore there could be infrared stable point in
right.
principle. Yes, and therefore coupling constant cannot be large. It is small in this case, and in my opinion,
Right.
it is useless after that to use strong coupling.
Right. This is not the case I'm doing here. I'm actually doing the case where NF is not of the order of NC, because this is the planar expansion. You're thinking of a Banks-Sachs type of fixed point. Now that is not the case here. I'm taking the case where NC goes to infinity, keeping lambda 2 finite and keeping NF finite over the 1. So these diagrams so the beta function does not have a 0, as you say. Those theories are also very interesting. In fact, they're probably more tractable precisely because the coupling constant is bound between a certain region. But these are not the ones that I'm talking about. I'm talking about large n QCD with an F finite, let's say. So.
No more questions? Let's